In this section, we're going to take a look at something called the critical section problem. So we kind of already have this idea, right, that with the concurrency, right, if I have two threads running at the same time, there is kind of an issue, right, where maybe they're doing stuff, to the same variable, same place in memory at the same time, and then there's this race condition, and sometimes things don't really work out the way we expect them to, right? We had issues like, oh, hey, I expected that one variable to be updated to, maybe the number 5, but instead it ends up being with something, different because somebody else wrote a value there instead of, what I expected. So what we're going to do is we're going to say, okay, as a way to fix that, right, what it would be nice is it would be nice to have basically a way to have different parts of my program that are protected. And that's what this critical section problem is all about. So we're going to define this, right, and then we're going to later on try to solve it. So here's the idea. For any particular program I have, I'm going to have basically a critical region and then an other region. So in a program, a critical region is basically, just picture it's somehow bounded, it's got a start and an end, right? Some number of instructions. And then that part of the program, that part is stuff that should only ever be run atomically or alone, right? So no other process should be doing stuff in a critical section when some other process is doing stuff there, right? So it kind of has this uniqueness property to it, right? So processes have this critical region, and the critical region is important or useful to us because we'll make the constraint that only one process can be in that region, right? And so on my computer, right, I'm going to have an entire set of processes, right? So I can have 1,000 things running, right? But at the end of the day, what we're saying is, okay, only one of you may be executing code in your critical region at any given time. And then after the critical region, right, there's just sort of other stuff, right? So there's other program code, and we don't really make any requirement on that, right? So that can maybe be executing at the same time. Another process is doing something in a critical section, or another, well, I should say thread. Another thread, right, is running some other code, right? There's no kind of requirement there. So basically what we're saying is I can divide my program into two pieces. One part I don't care about, it just can run whenever it wants. The other part I'll make the requirement that it can only run alone, right? Nobody else can execute critical code at the exact same time. All right, and this is with respect basically to a set of processes that is actually on your computer. So we'll use this kind of as our idealized model of how to protect stuff, right? Because if I'm able to force that this piece of code basically can only be executed by one person at a time, well then I'm going to have kind of this, I don't know if uniqueness is the right term, right? But in terms of the problem we talked about a second ago, right? The issue of the producer and consumer. For that problem, right, we had the issue where they were both changing counter at the same time. Well, now I can say stuff like, oh, counter should be a critical region, therefore only one of them will actually be allowed to make an update to it at a time, right? And so that kind of solves our problem. So this kind of definition here of this critical section, right, helps us to do a lot of things, right? Maybe somehow it's a brute force way, but it'll still serve as kind of a starting point for us to be able to solve concurrency issues. And we're actually going to try, right, with a couple of different ways. How do we actually, implement a solution to this? Now, one kind of note here that's really coming from the textbook is that for some systems, right, maybe your critical region somehow is denoted by, some system calls, right? Maybe that whole area, right, is stuff that needs to happen in terms of, the kernel API. Well, in that case, right, maybe sometimes we actually don't need to worry about having a specific mechanism, a specific algorithm in order to implement a critical region. Reason being is some operating systems are what we call non-preemptive, meaning that if somebody is, doing something in terms of the kernel, right, there is one process or one thread running, it's making some system calls, it's doing some privileged operations, that thing, right, cannot be stopped, right? Basically what you're saying is that once it starts doing something, right, once it starts using the kernel's infrastructure, right, it has to continue through, and nobody else can jump in there, preempt it, and go and either run on the CPU or make other calls on the kernel, right? So some kernels, right, are non-preemptive because, okay, I have a thread that's doing stuff in the kernel, right, and I don't want to basically be able to usurp it, right, and go do their own stuff because then the kernel gets left in a bad state, right? So generally when people go and do some kernel operations, you kind of want to let them finish rather than let other people get in their way. So that's kind of the motivation behind non-preemptive kernel, right? And if we had a non-preemptive kernel, then basically life is good, right? We don't have to worry about this critical region so much because our OS is already going to say, okay, this stuff all has to be executed together. I'm not going to let anybody else go in and do stuff that has to do with kernel calls at that time, right? But then, right, on the other hand, right, you have the stuff that does concern us, which is to say there are kernels out there, right, that do support preemption, right? So you can be doing whatever, right? It doesn't have to necessarily be, kernel code, right? It's basically saying that, for any kind of thread out there, right, at any point its operation can be preempted, right, and something else can run in its place. for those type of things, then we do have an issue, right? Because then we have the issue that somebody started to execute something, right, and they get, pushed off, right? They get, stored back as a waiting process, and then somebody else does stuff, and then we have these issues, right, of concurrency, right? So kind of think about that, and we'll talk about that maybe more, right? Is this idea of preemption versus non-preemption, right? The ability to pause a process, right, in its execution, and let somebody else execute instead of it, right? And there's maybe some reasons we'd like to do that, right? Like sometimes we have maybe a deadline, we want to make sure that something, exits out soon, so we kind of say preempt whoever's there and put the higher priority thing there. Or sometimes, right, whatever's running, maybe it's waiting for a resource, and really it's like, well, we really don't want you to wait on the CPU. We should let you go and put somebody else there. So there are other reasons, right? The preemption ends up being pretty a good thing kind of to support, and so we'll come back to that in a future section. So as we talk about ways kind of to address the critical section problem, we're going to have three basic parameters or behaviors, attributes, right? Let's be as generic as we can. We'll say three properties, right, of each solution, right? So these are three things that we have to have, right? Without these, we may have an algorithm that does something, but it's not going to be solving the critical section problem, which is what we care about, right? That's our general model of things. So the first thing we have to have is mutual exclusion. So basically, whatever it is my mechanism that I end up with, right, to solve this problem at the end of the day, the number one thing it must guarantee is that for any pair of processes, P1 and P2, only one may be in a critical region at a time, right? Execution of critical regions between those two processes is mutually exclusive, right? One, but not the other, right? Without this, we don't have anything, right? We're definitely not going to solve our critical section problem, right? We must have some way to guarantee that these things never happen at the same time. So this is going to be the first constraint, or the first, property, right, of the solution to this problem. The second thing that we care about is progress, right? So by progress, we mean this. I have, I'm basically allowed, right, in kind of definition of my problem, to have one process executing in its critical region at a time. If I get to a state, right, where nobody's in the critical region, and then somebody else, is basically waiting to enter their critical region and execute that code, then I should let them, right? I shouldn't make them wait around, right? I always want to be making progress, right? If I have CPU time available, right, if I'm ready to do work, then I should be utilizing it, right? I should have another thread, and that other thread, right, should be allowed to go on the CPU and do whatever needs to be done, right? What we don't want is we don't want to have a situation where we're executing one thread, and then we basically say, oh, even though I finished, thread 1, I'm not actually going to hand over control of the thread 2, right? Because I don't know, whatever, right? We don't want that situation, right? We want to be making progress towards the goal of giving everybody a chance to execute their code, right? So this is going to be our second requirement for solutions to this problem. The third requirement is something called bound waiting time, which is also very important. Basically, the idea is this. I can imagine I have my system running. There's a whole bunch of threads out there. Thread executes, thread executes, thread executes. But what if I have one thread that basically gets left behind, right? So there's a thread, that's basically been in the background, right? Running. But for whatever reason, it was never given a turn to enter its critical section, right? This is an issue. So what we also want, as kind of our last final property of a solution to this issue, is an algorithm that says, okay, I know that I'm going to get to you, right? So you have a set of processes, right? I know that I'm going to get to each of the critical regions in those processes in a fixed amount of time, right? So it's not going to be the case that 5 of those processes I get to pretty quickly in a second, right? And then that sixth process, right? Maybe I never even see it. Maybe it just stays in the background, waiting forever to enter its critical region, right? I don't want that. That would be an unbounded waiting time. What I want is a hard limit to say everybody's going to be able to execute their critical regions within this interval, right? Everybody will be able to go. Of course, an easy way to get there, right, is just to make everybody take turns, right? And then everybody kind of gets their fair share. So these are the three things, right? Mutual exclusion, progress, bound waiting time. Those are the three things that we're going to look at. We're going to make sure that our solutions to this problem, our algorithms, right, address those three things. Otherwise, they're not actually going to be able to solve the problem we're trying to solve, which is the critical section problem.